Hi all, let's see the next topic of Unit 5, Arithmetic Pipeline. In today's lecture, we are going to discuss about an introduction to arithmetic pipeline and then the concept of an arithmetic pipeline with the help of an example. So coming to the introduction, as we already know about the what is a pipelining. So pipelining is a technique of decomposing a sequential process into multiple sub-processes and executing the sub-processes in different stages of your pipeline. Already seen the concept of an instruction pipeline in the previous class, where the sequence of instructions are executed in the pipeline by overlapping the fetch, decode, and execute stages of your pipeline. So the next coming to the next type of a pipeline called an arithmetic pipeline. So an arithmetic pipeline, it divides an arithmetic expression or an arithmetic problem into various sub problems and execute them in different segments of your pipeline. And mainly, we are going to implement this concept of an arithmetic pipeline in a very high-speed computer where complex operations like if your floating point arithmetic operations are being implemented. So they are used to functions such as the floating point operations, such as addition, subtraction, multiplication, division, as well as a fixed point multiplication and division operations. And these type of operations are encountered in the scientific problems. Now let us see an example of how this arithmetic pipeline performs an addition and subtraction operations on two floating point numbers. So let us consider an example. We have two floating point numbers on which a floating point addition or subtraction operation has to be performed. So consider I have the values of x and y, where my x is my first floating point number and y is the second floating point number, which is of the forms a into 2 to the power of a and b into 2 to the power of b, where capital A is said to be called as the mantissa part of my operand and the small a represents the exponent. So I have a x value in the form of 0.9504 into 10 to the power of 3 and y in the form of 0.8200 into 10 to the power of 2, where a and b are my fractions that represent the mantissas and small b are the exponents. So the floating point addition and subtraction using an arithmetic pipeline, it is divided majorly into four segments, and each segment contains a corresponding sub-operation that has to be performed in a given pipeline. So we are overall you are dividing this arithmetic floating point addition and subtraction into four segments, and each segment is going to be executed on each pipeline stage by overlapping the stages of your pipeline. So the sub operations, it is divided into four segments. The first segment you are going to compare the exponents by performing a subtraction, and next you are going to align the mantissa part of your data and add or subtract the mantissas, and finally you normalize your result. The same steps what we have seen in your floating point addition and subtraction operation. Now we are going to implement the same concept in the form of a arithmetic pipeline. So let us see. So this arithmetic pipeline has four segments: segment 1, segment 2, segment 3, and segment 4. The output of one segment is given as an input to the next segment so that it completes the operation. So consider in the first segment you need to compare the exponents. Normally when you consider any two floating point numbers, you cannot directly perform an addition or subtraction operations on those two numbers directly because the powers, the exponents are different. So you have to first align the mantissa part of your data in such a way that the exponent of both of your fractions are same. So for that you need to compare the exponents by performing a subtraction operation. So the difference in the exponents will tell you about how many times the mantissa of the first exponent has to be shifted towards the right in order to align the mantissa part. So the first thing is you need to compare the exponents. Based on the difference, you have to align the mantissa part of your least exponent. Next, that particular output is written into R. So A and B represents the mantissas of your fraction and small a and small b represent your exponents. They are stored in a temporary register R. From there, it is given as an input to a segment 1. So in segment 1, we are going to compare the exponents by performing a subtraction, and the difference is given as an input to this particular segment, where based on the exponent, you are going to align your mantissa part of your mantissas, and the result will be stored into this temporary register. So that is second segment. Second segment is you need to align the mantissas. In the third segment, you have to perform an addition or subtraction on the mantissa part of your data. Your aligned mantisas are stored in a capital R, where you have to perform an addition or subtraction operation, and the result is again stored into the temporary register R. That is your segment 3. In segment 4, you are going to normalize your result. The normalization involves adjusting your exponents in such a way that the result is said to be in a normalized form. So this is how you perform a floating point addition and subtraction operations using an arithmetic pipeline. Now let us see it with an example. So first step is you are comparing your exponents by performing a subtraction. So the larger exponent is chosen as an exponent of your result. And the difference between the two exponents, which is 3 minus 2, if you consider this as an example, so this is my example. So the larger exponent 3 is said to be called as your result of your exponent. So you have to make this particular exponent also equal to 3. So for that you have to first perform a subtraction of the exponents 3 minus 2. So that based on the difference of the exponent determines how many times the mantissa associated with the smaller exponent must be shifted towards the right in order to align the mantissa part of your data. So 3 minus 2, 1. So you have to perform one right shift of the corresponding y value so that your exponent and increment your exponent by 1 so that it becomes 10 to the power of 3. So the second step is aligning the mantissas. So in this step you are going to perform shift operation associated of the mantissa associated with the smaller exponents to the difference of the exponents determined in the step 1. So in step 1 we are getting a subtraction operation, the result as 1. You have to perform one shift towards the right in order to align the mantissa of the second fraction y. So this y, you are not doing anything with this. This is the result of your exponent. For the y part, you are going to perform a right shift 0.0820 into, you are going to increment your exponent by 1 into 10 to the power of 3. Now your mantissas are aligned in such a way that your exponent of both of your fractions are the same. Next, we go for the third step. In the third step, you can perform either add addition or subtraction operations on the mantissa part of your data. So the two, in this case, I am performing an addition operation. So the two mantissas are added in this particular segment. So x plus y, which gives the result 0.9501 is my first fraction and 0.08200 is my second fraction. I want to perform an addition into 10 to the power of 3 is the exponent of my result. So if I add this two, I get a value of 1.0324 into 10 to the power of 3. This is my result. So once you get your result, you have to check if the result is in a normalized form or not. If the result is not in a normalized form, you have to normalize the result. That's what we already done in floating point addition subtraction operation. The same thing applies here. So the fourth step is normalizing the result. So here your result is not said to be in a normalized form. There is a condition of overflow situation. So what do you mean by overflow? If you have 1 in this particular position, we mean to say that that is not a normalized result. So you have to have a 0. You should not have a non-zero value. You have to have a 0 here in this particular condition, in this particular situation. So we have to shift this 1 towards the right. So since this is an overflow situation, so you have to, in order to normalize this particular result, you have to perform a right shift and increment the exponent by 1. So your result becomes z, stores your result, z value becomes 0.10. This one will be shifted towards the right. So it becomes 10324 into 10 to the power of, you perform an increment on your exponent, it becomes 10 to the power of 4 because you performed a right shift. So this is how you perform a normalization. So this is how you perform a floating point operation at addition or subtraction operations on two floating point numbers by implementing a concept of arithmetic pipelines in such a way that it is divided into, the entire operation is divided into multiple segments and they are executed by overlapping the all the segments of the pipeline. Thank you.